Pluto, a remote and baffling world, was once a single and dependable planet in our solar system. However, recent discussions among leading astrophysicists, including Neil deGrasse Tyson and Michio Kaku, have brought Pluto back into the spotlight with astonishing discoveries. These scientists have suggested that Pluto's orbit may eventually intersect with Neptune's, an idea that raises questions about how such a collision could occur and what the consequences of such a massive event might be. Could this lead to a fascinating and rare phenomenon, or is there more to this potential planetary impact? Join us as we delve into the possible outcomes of a Pluto-Neptune collision. Pluto, once thought to be a planet in its own right, is now relegated to a smaller classification due to its peculiar orbit and its status as a dwarf planet. Despite its demotion, Pluto remains a subject of interest and research within the scientific community. Recent examinations by leading astronomers show that Pluto's orbit is dangerously close to Neptune's, raising alarms among astrophysicists like Tyson and Kaku about the possibility of a catastrophic collision between the two. But how could such an impact happen? Unlike other planets in our solar system, Pluto follows an eccentric path around the Sun, taking a staggering 248 years to complete one full orbit. Since its discovery in 1930, Pluto has not even completed a single orbit around the Sun. However, the intrigue surrounding Pluto doesn't end there. Its orbit is characterized by a highly elliptical shape, unlike the nearly circular orbits of the larger planets. What makes Pluto's orbit even more puzzling is its inclination. Pluto's orbit is tilted at an angle of 17 degrees to the plane of the solar system, adding complexity to its orbital dynamics. This tilt, combined with its irregular shape, makes Pluto's orbit significantly more chaotic compared to other planets. One of the most fascinating aspects of Pluto's orbit is its relationship with Neptune's orbit. For approximately 20 years of each orbit, Pluto actually comes closer to the Sun than Neptune does, contrary to what one might expect based on their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets in the solar system. When Pluto's orbit was first studied after its discovery, astronomers struggled to understand its peculiar trajectory. Unlike the orbits of other planets, which lie close to the ecliptic plane, Pluto's orbit stands out due to its steep tilt and elliptical shape. The mystery surrounding Pluto's orbit deepened when it was observed that its orbit does indeed cross that of Neptune's. This apparent paradox is resolved by the complex gravitational dynamics of the solar system, specifically through a phenomenon known as the three-body problem. The three-body problem in astronomy is the challenge of predicting the motion of three objects, like Pluto, Neptune, and the Sun, that influence each other through their gravitational forces. The interactions between these objects create a dynamic system that is difficult to predict, as each body affects the others in a constantly changing manner. For Pluto, this three-body problem explains why its orbit is stable despite crossing Neptune's orbit. One key concept that keeps Pluto's orbit stable is libration. In the case of Pluto and Neptune, this term refers to the phenomenon where, whenever Pluto crosses Neptune's orbit, the two planets are always at least 90 degrees apart. This spatial separation is crucial in preventing the two bodies from colliding. Another important factor is vertical libration, which refers to the vertical movement of a celestial body within its orbit. For Pluto, this means that when it comes close to Neptune, or any other large planet, it remains positioned well above or below the plane of their orbits, adding another layer of protection against potential collisions. A third concept that stabilizes Pluto's orbit is VZK wobbling, named after the three scientists, Vashkov, Zaltz, and Kulikov, who studied how celestial bodies move in space. This phenomenon refers to the way Pluto, Neptune, and the Sun influence each other through gravity, causing slight changes in their positions over time. For Pluto, VZK wobbling explains why its orbit, despite appearing unpredictable, remains stable. These forces help maintain Pluto's orbit for incredibly long periods, possibly even billions of years. Although Pluto's orbit is chaotic in nature, these gravitational effects from other planets help keep its trajectory stable in the broader context of the solar system. These forces play a vital role in preventing planets and other celestial bodies from colliding with each other. Without these stabilizing factors, the solar system would be a far more chaotic place, with planets and dwarf planets potentially colliding or being ejected from their orbits, causing a cascading series of events. For Pluto, this stability is especially significant given the ongoing discussions about a potential collision with Neptune. Understanding Pluto's orbit provides us with insights into the dynamic nature of the solar system. It serves as a reminder that even the most seemingly unstable orbits can achieve a state of harmony through the intricate dance of gravitational forces and orbital mechanics. The study of Pluto's orbit also highlights the need for continued research and observation to better understand the forces that shape our solar system. The case of Pluto illustrates the importance of studying the erratic nature of celestial bodies and the role that gravitational interactions play in their movements. The concept of orbital resonance, which refers to the delicate balance of gravitational forces that govern the orbits of celestial bodies, is clearly demonstrated by Pluto. Even small changes in its position or velocity can significantly alter its long-term orbit. In the late 1980s, computational simulations provided valuable insights into Pluto's orbit. These simulations showed that, despite the stabilizing effects of phenomena like libration, Pluto's orbit can still be highly unpredictable. A tiny deviation in its initial conditions, such as its position or velocity, could result in dramatic differences in its path over millennia. Nevertheless, these models also showed that Pluto's orbit remains generally stable over billions of years, suggesting that its journey around the Sun follows an underlying order, even if it appears chaotic. However, these simulations also revealed the challenges of making precise long-term predictions. The three-body problem, combined with the system's sensitivity to initial conditions, means that predicting Pluto's future trajectory is a complex and uncertain task. While simulations provide a useful tool for understanding and forecasting the behavior of celestial bodies, they are limited by the accuracy of the initial data and the complexity of the forces at play. These challenges are underscored by the fact that large orbits like Pluto's tend to be turbulent and difficult to predict. The case of Pluto's orbit serves as a reminder of the ever-changing and dynamic nature of the universe. While we have made significant progress in understanding space, Pluto's case highlights how much more we still have to learn about the gravitational effects of the giant planets, such as Jupiter, Neptune, and Saturn, which play a crucial role in shaping Pluto's orbit. Their presence and positions have far-reaching implications for the stability and trajectories of other bodies in the solar system. This brings us to the question: why are prominent astrophysicists like Neil deGrasse Tyson raising concerns about a potential impact between Pluto and Neptune, despite all the complex forces working to prevent such a scenario? Tyson, a renowned astrophysicist who played a significant role in Pluto's reclassification from a planet to a dwarf planet, offers an insightful perspective on the evolving nature of celestial mechanics. Tyson argues that, while Pluto's orbit is stable for now, it could undergo significant changes in the future. This possibility underscores how much more we still need to learn about the forces that govern our solar system. Tyson's views on Pluto's reclassification and its current status as a dwarf planet are rooted in the ever-expanding understanding of our solar system. He believes that this reclassification is not a demotion but rather a necessary adjustment to our growing knowledge of the diverse bodies orbiting our Sun. His approach to celestial mechanics is one of ongoing learning and adaptation. Tyson acknowledges the complexities of Pluto's orbit and its interactions with Neptune while recognizing the inherent unpredictability of space. He suggests that, although Pluto's orbit has been relatively stable for billions of years, there is always the possibility of unforeseen changes. As we continue to study the forces acting on these distant bodies, new discoveries could challenge our current understanding. The complexity of Pluto's relationship with Neptune is an excellent example of how even well-understood orbital dynamics can be subject to future revisions as our knowledge evolves. Moreover, Tyson's observations on Pluto's orbital resonance with Neptune, where Pluto completes 2 orbits for every 3 of Neptune's, demonstrate how delicate and finely tuned the mechanics of the solar system are. This resonance maintains Pluto's stability by preventing it from coming into close proximity with Neptune, a critical factor in the continued stability of both planets. In conclusion, Pluto's orbit is a fascinating case study in the dynamic nature of the solar system. It highlights the delicate balance of gravitational forces that govern celestial bodies and the ever-evolving nature of our understanding of space. While the likelihood of a Pluto-Neptune collision is currently low, the complexities of their orbits serve as a reminder of the intricate and interconnected forces that shape the universe. As scientists like Tyson and Kaku continue to explore these phenomena, our knowledge of the solar system will undoubtedly deepen, offering new insights into the mysteries of the cosmos. Pluto's orbit is a profound reminder of the interplay between stability and chaos within the solar system. While current models suggest a low probability of a direct collision with Neptune, the intricate forces that govern their interactions remain a field of active study. Astrophysicists and astronomers use Pluto's case to better understand the dynamic systems that govern the entire cosmos. These studies also emphasize the fragility of celestial mechanics and the importance of precise measurements when predicting long-term orbital behavior. The implications of a Pluto-Neptune collision, however unlikely, would be monumental. Such an event could potentially reshape both bodies, altering their orbits and even affecting the gravitational equilibrium of the entire solar system. While simulations show that current resonances and stabilizing forces would prevent such an occurrence for billions of years, this does not preclude the possibility of future changes caused by external forces, such as the gravitational influence of a passing object or changes in the solar system itself over eons. Moreover, studying Pluto's orbit has implications that extend beyond our solar system. Many exoplanets and distant celestial bodies discovered around other stars exhibit similar irregularities in their orbits. By understanding the forces that stabilize Pluto and prevent it from colliding with Neptune, scientists can apply this knowledge to study planetary systems far beyond our own. This contributes to our growing understanding of how planetary systems evolve and how stable configurations are maintained. Pluto's story also serves as a symbol of scientific progress. Its reclassification from a planet to a dwarf planet ignited public debates and revealed how deeply people connect with celestial bodies. Yet, this redefinition was not a dismissal of Pluto's importance, but rather an acknowledgement of our growing knowledge about the vast diversity of objects in the solar system. The discovery of other dwarf planets, such as Eris, Haumea, and Makemake, added depth to our understanding and reshaped our classifications to reflect this complexity. Neil deGrasse Tyson and other astrophysicists continue to champion the importance of adapting our perspectives as new data emerges. Pluto's reclassification reflects the ever-changing nature of scientific discovery. It shows that, even when the status of a celestial body changes, its scientific significance and the mysteries it holds remain as intriguing as ever. As missions like NASA's New Horizons probe, which flew past Pluto in 2015, continue to provide data, our understanding of this distant world grows. Observations of its surface, atmosphere, and moons, such as Charon, offer new perspectives on the nature of distant celestial bodies. Each discovery further deepens our appreciation for the complexity of Pluto and the solar system as a whole. In the coming decades, advancements in technology and observational methods will allow scientists to simulate and predict the long-term behavior of celestial bodies with even greater precision. Pluto's orbit will remain a critical case study in these efforts, teaching us not only about its unique dynamics but also about the broader forces shaping planetary systems across the universe. Ultimately, Pluto's tale is one of resilience, intrigue, and the relentless pursuit of knowledge. From its discovery in 1930 to its demotion to dwarf planet status and its continued study by leading astrophysicists, Pluto represents the enduring spirit of exploration. As we continue to peer deeper into the cosmos, Pluto will undoubtedly remain a focal point of fascination and a key to unlocking the secrets of our solar system and beyond.